Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 65. So for the past 4 sessions, we've been having some tutorials wherein we were discussing about selection rules, and also I had given you some clarifications related to previous lectures. Okay, so we'll continue with our regular lecture sessions from here onwards. Okay, so where are we in the course, right? It's very easy to, as they proverbially say, right? Miss the forest for the trees. Okay, so what we shall do is I shall first give you a very small recap of where exactly we are in this course. So where are we in the course? I mean, it's especially important in a course such as astrochemistry, which is highly interdisciplinary, and it also therefore involves fundamental science from different branches. For example, some examples of spectroscopy, statistical thermodynamics, quantum mechanics, etc., etc. Okay, all right. So where are we in the course? Broadly speaking, what big module are we in? We are as part of detecting the molecules. In space, of course, right? So, as part of detecting molecules in space, well, we saw that spectroscopy, right? Some quantum mechanics, abbreviated here it is quantum mech, and a little bit of statistical thermodynamics. We didn't see much, but very little. Okay. We saw this especially in the context of the LTE, that is the local thermal equilibrium, and other ideas. And so therefore, until now, we've been looking at a big, broad view of all these areas as related to astrochemistry. Okay, right? So we've been having a broad view of spectroscopy, quantum mechanics, and statum as needed for astrochemistry. All right. So the thing is, but this is not all, right? Ultimately, we have to detect the molecules where in space. So therefore, the idea is that it is by using the idea of astronomical spectroscopy that we detect molecules in space. Okay, right? We detect molecules in space via astronomical spectroscopy. And the spectroscopy part, of course, right, we've been seeing for quite some time now. So now it's time to look into some astronomical aspects, right, associated with detecting molecules in space. Okay, so that is what we shall be spending time on for the next few lectures. So what we shall be looking at now is the astronomical aspects of, in fact, I'll be more careful. I'm telling key astronomical aspects, right? Because astronomy is an exhaustive area of in its own right, as you all know. So therefore, there is a separate subject called as astronomy. In fact, several physics departments have been titled departments of physics, astronomy, and astrophysics, correct? Right? So therefore, we shall only be looking at key astronomical aspects as relevant to detecting molecules in space. Okay, so key astronomical aspects of detecting molecules in space. Okay, where do we begin with? Well, let's actually begin with some challenges, okay, right? So I'll illustrate to you two important astronomical challenges in detecting molecules in space. Now, what is the first one? So recall, how is it that we are going to be detecting molecules in space? Well, by getting a sample of light, right, which contains information about the molecules present in space. And when I say collect light, I'm effectively talking about have a telescope and a spectrometer setup attached to it and get some waves, right? And compare the signals with what is obtained on Earth, right? If the two spectra exactly match, if the signals match, we understand that, oh well, whatever molecule we know on Earth, right, is also present in space, okay? But there's a key caveat. How do you know where the light actually came from? In other words, did the light actually come all the way from space, right? I mean, from some part of the ISM, or what if it is simply coming from the Earth's atmosphere itself? We do understand from high school knowledge, right? I mean, it's very well established now that the Earth has an atmosphere, which is why we're all alive, which is why life is even possible, right? The atmosphere blocks out a lot of harmful rays, which can cause cancer and other bad effects to human beings and other life forms, right? So what is this atmosphere? It contains 7 layers, the troposphere, stratosphere, blah, blah, etc., etc. And we have a lot of gases over there, right? A lot of gases, which act as an effective shield against harmful radiation, correct? Okay, but the atmosphere also contains a lot of molecules, right? So when we are on Earth, right? See, the atmosphere is above us. So when we are on Earth, and as we know, like obtain signals, how do we know there is no interference from the molecules present in the Earth's atmosphere? Or how do we know that the molecules are actually coming from space, so to speak, or just from the Earth's atmosphere? So one of the first challenges is interference from the molecules present in Earth So this is a major source of problem. Okay, please note it. Right. Now, this is in fact why I think I may have briefly mentioned it, but now is the time to slightly elaborate a bit more. What were the first molecules to be detected in space? Yes, CN, CH plus, and CH. What would we anticipate? Beyond hydrogen, beyond H2, helium, etc. What do we anticipate? We would perhaps anticipate that water, if not in the liquid phase, at least in gaseous phase, we must be able to detect it, right, from space. But water was not detected at all. Why is it? For a long time. I mean, of course, water was detected, I think around 1976 or 76 or so. But for a long time, water was not detected. Why do you think it was so? It is because of this fact. The atmosphere of Earth contained a lot of water molecules in itself, right? So therefore, the signal, right, the signal obtained from space, which was due to water molecules, had interference from the signals obtained due to water molecules present on Earth's atmosphere. So its detection was very hard, okay, right? So illustrating this aspect, so as an example of highlighting how difficult it is due to the presence of the Earth's atmosphere, H2O detection in space, predominantly ISM, not so easy. It took until I think around 1976 to definitively identify, to identify water in space. All right. So please note this, okay? So the interference from the Earth's the molecules present in Earth's atmosphere is a very great challenge. In fact, that is why, when you think about all these observatories, all these observatories which are constructed to get the signals. We're talking about the various telescopes. For example, ALMA, the most famous one, right? Or VLBA in ALMA is in Chile. VLBA in Hawaii, I think. Okay, Hawaii, USA. And what about India? You talk about the various astronomical observatories such as Aries in Nainital, and then IAO, IAO in I think Ladakh, Hanlu or Hanli, yeah, one of those places. They're all located in deserts. Okay, right? So important that the astronomical observatories are set up in regions of low humidity, and then and where the pressure is also low. And what is the pressure due to? It is due to all the molecules, right? So when the pressure is low, we understand that in the high altitude regions, the number of interfering molecules are also going to be lower. Okay, right? So one way to tackle this problem, one way to address. So one way to address this issue of interference, right? Interference from the molecules present on Earth's atmosphere is to have the astronomical observatories in high altitude, low humidity places. Okay. What are some examples of such observatories? As I just told you, VLBA in USA, ALMA is very famous in Chile, and in India itself, we have like Aries and this thing, IAO. So I'll leave it to you as homework to actually, get the expansion for all these acronyms over here, right? What is IAO? What is Aries? Aryabhata, right? Yeah. ALMA, Atacama, right? It's in the desert. And VLBA, very large. Okay, right? So I'll leave it to you as a homework. Expand all these things, okay? So that is something you can easily do, all right? Just look up and figure out what all these things mean. This doesn't completely solve the problem, but what it does do is it vastly reduces the interference, okay, due to molecules present on space. Molecules present in the Earth's atmosphere, okay? All right. Now, this is the one basic challenge. What is yet another challenge? It's of course also due to the presence of Earth's atmosphere, but it manifests itself in a completely different way. Let's see what it is. So the other problem is, so this was the first challenge, point A, and the other challenge is actually that the molecules in Earth's atmosphere, what do? They of course, there is a direct interference in the form of, like signals from the molecules present in the Earth's atmosphere versus, like the same molecule, if it is present in space, right? So there is an interference in the form of signals, but there is also interference in that the molecules in Earth's atmosphere can cause the scattering of light obtained from a star. Do you understand what's happening here? So the molecules don't just directly interfere and can sometimes result in false positives. That is, you may think that a molecule which is actually present in space is in reality not there, but just that the signal we obtain might just be from the Earth's atmosphere. Okay, right? So that is direct interference. Alternatively, it can also cause indirect interference by leading to scattering of light obtained from stars. We've all heard this poem, right from childhood. Twinkle, twinkle, little star. Why is it that the stars appear to, just twinkle or shimmer or shine? It is because, not shine, but twinkle, okay, right? It is because of the scattering of light due to Earth's atmosphere. Okay, right? But why is it a problem? Well, it's a problem because it affects, it's a problem because affects the resolution. I'll more precisely define the phrase resolution in a bit, okay, right? But it affects the resolution of the spectral signals. Okay, right? So what happens is the waves, right? The waves will become more blurry. What do you want ideally? You want the radiation, that is the light obtained from a star, to be emitted to you, right? Now, if it is emitted to you, what is the meaning of emission? It is coming to you in a straight line. But because it is getting scattered, right, you have a problem with the signals. You don't get, like beautiful, like discrete lines, even taking into account the lifetime of spectral lines, right? The natural width of spectral lines due to the finite lifetime of excited states, due to various phenomena. I think we looked into that probably some 10 lectures earlier, right? So notwithstanding those things, we shall not be getting proper spectra. So therefore, it shall be very difficult to actually, get proper spectral lines. Okay, so that's why scattering is a problem. Are we clear? I'll just write it down more precisely. It is that, in other words, for us to record spectrum, to obtain, I would say, not record, sorry, to obtain spectra from space, emission of radiation is important. Emission of radiation, right? I mean, by the molecule in space, okay, right, is key. What scattering does is, what scattering ensures is that instead of, like us getting focused lines, it results in us getting very blurry spectral lines. And so this would become a natural problem, right? If you're not even able to get proper lines, how will we be identifying molecules? All right. So this is the problem with scattering. Now, on this note, I would also, take you through a small detour, but an interesting one nonetheless. It is that we've all heard, as perhaps in high school or something like that, we've all heard that what is one way to distinguish between a star and a planet? See, sometimes to the naked eye, planets such as Venus and Jupiter, especially, these two are routinely, they could be easily seen in the sky, right? What do we think are of the features? What distinguish between stars and planets when we see through a naked eye? Do we have an answer? The answer is that planet normally, a star typically twinkles, right? We see this twinkling of a star. But then the planet, whereas is typically very dim. It looks like it's a dim, dim, sad body over there. But the star looks like it's happily twinkling, right? What is the cause of it? Any idea? Of course, we now understand that it is due to the scattering of light. It is due to the scattering of light that the stars twinkle. But the planets should also be, scattering light, right? But why don't they twinkle? This is just a nice, interesting scientific aside, okay? Why is it? Well, it has to do with the distance. I'll explain to you. So note that stars and planets both do scatter light, but the stars appear to twinkle, whereas the planets don't. Okay, well, this is don't. Written it very badly. What is the cause? The cause is that the stars are much far away. I mean, it's an obvious fact. The stars further is in fact an understatement. They are much further away vis-a-vis the planets, right? Than. But what happens is that as a consequence of this, okay, right? Consequently, the stars, the light beam, that is coming from the stars, that is much narrower. In other words, it appears as though, like the star is like a point source, okay, right? Stars act like point source of light. So the light beam is much narrower, right? As a result, the scattering effect is much more pronounced, okay? Light beam is much narrow, and which implies that scattering is more pronounced. Whereas with planets, because the planets are much closer by, the light beam appears to be thicker, right? So the light beam emanating from all possible directions in planets, right? They are much thicker, but from planets, you have a thicker beam of light. So the scattering not so pronounced, okay? So scattering not so pronounced. And hence, what you observe that the stars actually scatter. I mean, the stars scatter and twinkle, but while the planets also scatter due to a much thicker beam of light reaching us, the twinkling effect is not so pronounced, okay? So please take into account these two challenges. Now, therefore, considering these challenges, right, when we actually observe the molecules on Earth, right, when you actually make observations from Earth, when our objective is to detect molecules in space, we need certain windows, okay, right, or certain regions of the electromagnetic radiation, some region of the electromagnetic spectra, wherein the Earth does not receive radiation from the atmosphere. Are we clear? In other words, see, normally we would want the atmosphere to protect all of us, correct? Because there are very harmful ultraviolet, X-ray and gamma ray radiations, etc., which the sheet of atmosphere protects us from, correct? But in the case of a poor astronomer who's trying to detect what molecules are present in space, the same concept is actually deleterious to this astronomer's professional existence, okay? So what we instead need is, we need some holes to the sheets. I mean, of course, not artificially created, just some holes which allow some radiation, okay, right? Some radiation from outer space to pass through the atmosphere, so that we do get some information about the molecules which are available in outer space, okay? So we come up with what is called as the concept of atmospheric windows. So we need the idea of atmospheric windows, which are basically wavelengths or frequencies of wave numbers, wavelengths wherein interference from Earth's atmosphere is minimal. Now this is measured by what is called as opacity. Okay, I'm not going to give you the formula and further details, but by the opacity is a measure of what atmospheric window might be suitable to detect molecules in space. Okay, now as it turns out, there are four major regions, okay, via which you can actually detect molecules in space. Okay, so these atmospheric windows are to detect molecules in space. To detect molecules in, to detect molecules in outer space. Okay, so that's why we need these atmospheric windows. So broadly speaking, there are four famous, or I would say, conventional, four conventional atmospheric windows which can be used, right? When I say atmospheric windows, these are nothing but some wavelengths, okay, right? Some specific wavelengths in the electromagnetic radiation which are conducive for the detection of molecules, okay, right? So there are four atmospheric windows which can be used. To detect molecules in space. All right. So I think, with that, I'll just summarize the content we saw in this lecture, and I'll continue from this particular aspect in the next lecture. So what did we see in this lecture? We saw that we had to also discuss some astronomical aspects of detecting molecules in space. And having said that, we started off with two key challenges, part of detecting molecules in space, two key astronomical challenges. One was the direct interference of the molecules present in the Earth's atmosphere, right? And the next one was the atmosphere causing the scattering of radiation obtained from outer space. Okay, and so as part of it, we also saw that the observatories present, right? The observatories present are present on Earth better be located in areas which have like low humidity and high altitude and low pressure regions, etc. And we also saw that this phenomenon of scattering, is more pronounced in the case of stars, but not so much in the case of planets due to the distance of the stars being much further away effectively. Okay, so then I said that these two challenges give rise to what are called as atmospheric windows, which can be used to detect molecules in space. So I said, broadly speaking, there are four windows about which we shall be seeing in the next class. Okay, thank you so much. Have a good day.